turn off my fog machine. Here, Brandon. Here you go.
Oh, thank you.
Okay, there you go. Oops. All right. Yes, all right. Okay, so now it's back to business. It's business as usual. We'll finish off chapter 8 and then start chapter 9. Okay. Yes, all right. So we left off in the very end of chapter 8 where we talked about resonance, calculating bond order. So we've gotten to our second way to calculate bond order, and that's for resonance structures. The idea that, okay, yeah, you can see single and double bonds in a structure, but sometimes those double bonds are in more than one place. So for example, benzene, I showed you before, we can see has 3 double bonds and 3 single bonds. But the idea with benzene, what makes it really, really stable is that those double bonds are actually smeared across the entire molecule, that they can appear in these 3 locations and equally as likely to appear in these 3 locations. So we don't say that benzene has 3 double bonds, 3 single bonds, but instead those double bonds are smeared across the entire molecule. So all of those carbon-carbon bond lengths and bond enthalpies are the exact same, that we don't have 3 short bonds, 3 long bonds. No, they're all the same bond length. So we calculated the average bond order for these carbon-carbon bonds by this resonance structure calculation, where we count all of the bonds involved in the resonance structure. So you can look and think, oh, these double bonds kind of move across the entire molecule. So if you count all the bonds, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds moving across how many different positions are there? There are 6. So we see 9 divided by 6 is 1.5. So we see that carbon-carbon in benzene does not exhibit all single bond character, not all double bond character, but instead all the carbon-carbon bonds. Oh, another costume. Very good, nice. Is a carbon-carbon bond length of a 1.5. So we see these carbon-carbon lengths are a little bit stronger than a single bond, but not as much as a double bond. And so here's another example of resonance structures, and then this was our last slide we went over, but I'm going to go over it again anyway, of other common resonance structures, and they all kind of have the same deal going on. All of them have an oxygen minus somewhere in the molecule, and the idea is, like, I can place this double bond here, or I could place it here and make the minus sign over here, or I could place the double bond over here. So the idea in carbonate is that double bond has 3 different positions that it can exist in. So we see there's 1, 2, 3, 4 different bonds that are moving across 3 different positions. So we see that carbonate actually has a CO bond order of 1.33. And then we looked at another example, acetate. We got to be careful here and think about, okay, where can that double bond go? We're always delocalizing that double bond. The double bond can go here with this oxygen, or I could put the double bond here on this oxygen, and then the minus sign will be over here. But can I put the double bond between these 2 carbon atoms? No. So this example is a little bit different because that carbon-carbon bond cannot participate in resonance. It's only between the carbon and the oxygen. So we see in this example, let me just erase all this stuff. Go back to the original molecule. There's 1, 2, 3 different bonds. Over how many positions are they moving? 2. So we see that in this example, CO has a bond order of 1.5. All right, and so that is a common exam question where I would say something like, in which structure, carbonate or acetate, is the CO bond longer, or something like that, where we understand that longer bonds typically mean smaller bond orders, so we're looking for the resonance structure with a smaller bond order. So in that case, we have to draw the molecule, we have to predict its bond order using the resonance structure, and then finally using the relationship as bond order goes up, strength goes up, but length goes down. So large bond orders are typically short bonds. And then we looked at, here's another example, this is sulfate. All right, so we see here that the double bonds kind of here on the top and bottom between sulfur and oxygen, but if you think about it, there's a lot of different places those double bonds can go. So there's 1, 2, let me count this, 1, 2, 3, 4, 5, 6 different bonds. But then how many different positions can those double bonds go? 4 different positions. So we see 6 over 4. So we see that the sulfur-oxygen bond order is about 1.5 in this example, all right? Because we can have different places to place that double bond, all right? And so all of these kind of have very similar characteristics about them. They all involve oxygen, and they all have this like negatively charged oxygen attached to it somewhere where we can make different places to place that double bond. Versus formaldehyde, we do see a double bond in formaldehyde, but can we place this double bond anywhere else? Can I put it right here? No, because hydrogen never makes more than one bond, and we can't put it there. So this double bond is actually fixed in one place. This structure cannot undergo resonance. So what is the bond order between the carbon and oxygen here? Do we have to do the resonance calculation? No, we just say that carbon and oxygen, this is a bond order of 2 because it's a double bond, that's it, all right? So that's a really good question where I could give you carbonate, acetate, and formaldehyde, and I ask you which one has the longest CO bond? Longest CO bond length. And so in your mind you think, oh, you want the CO with the smallest bond order, and so in that case it would be carbonate would have the longest CO bond order. Even though, you know, it looks like it's all single and double bonds, we have to include the idea of resonance in carbonate and acetate, but not in formaldehyde. Formaldehyde would have the shortest bond length because it has a bond order of 2. Right? And so that's the end of chapter 8. We're going to talk about resonance a little bit more in chapter 9, and we'll talk about the third way we calculate bond order. All right, so, okay, so on to chapter 9. So chapter 7 homework, right, was due. Was it due? Yeah, it was due. So chapter 8 will be due on Monday. And so hopefully this weekend you did practice those 6 steps to Lewis structures. That's a very important skill. Sometimes we give you structures on the exam, sometimes we don't, and it's up to you to draw the structure. My 6 steps, they are foolproof. So if you learn the 6 steps, then you'll be good. So keep those 6 steps in the back of your mind because we're going to be using them a lot in chapter 9. And actually, I forgot, I wanted to make a small announcement about lab because most of you, like Wednesday, Friday, Monday labs, you're doing gas, right? The gas lab. And that is your last in-person lab of Chem 1210. Yay. Yay, sure. But then there's one more lab. It's digital, it's MGB. It has to do with chapter 9 stuff. Well, this gas lab is a really great lab to do in the lab space because it's really interesting and it's kind of like a create your own adventure type, like solve some type of problem type of lab where you investigate this challenge yourself. And so just because gases, we're not learning about gases until chapter 10, so there's no way we're going to be able to review it before you do the lab. I just wanted to give some tips for this lab, and the one tip is they talk about percent recovery a lot in that lab because you're going to make this like really janky apparatus to collect a gas. It's not very good. The apparatus for you to collect your gas, you're not going to collect all the gas in your reaction. So the first couple trials that you do using that apparatus, you're going to calculate the percent recovery of your specific apparatus. Let's say that you can only collect like 75% of the gas that your reaction produces. So in the lab, they call this percent recovery, but to relate it to something we already know, just think about that as percent yield. All right, percent recovery is essentially percent yield, where we learned that percent yield is your actual yield over your theoretical. So that theoretical yield, this comes from stoichiometry, right? You know how much stuff you react, all of it makes products, you can calculate how much gas you make. That goes in the denominator, but then you go to actually do the experiment, but you only collect you know, a little bit less than that. That's your actual yield. This is what you actually collect in lab using that apparatus. All right, and so that's a certain percentage. You're not going to get 100% recovery because your thing's very janky. All right, so you're only going to get, like, let's say 60% of the gas that's produced. So just think about it like percent yield. It's no different. Actual is what you actually are measuring and collecting in lab. Your theoretical yield, which may be in liters or it might be in moles of gas, you get this from stoichiometry from your starting materials because you'll weigh those out. Right? So that's relating percent recovery to something we already know. It's just percent yield. I've already posted chapter 10 slides, so if you want to look at those gas slides to help you with this lab, you can. But basically, you're just going to be using this equation, PV equals nRT, where we can relate the pressure of the sample, so typically that's the pressure of the room, the temperature of your sample. We can relate how many moles of gas is produced to the volume that it occupies. So volume is what you're measuring using your apparatus. Pressure comes from atmospheric pressure. Temperature is the temperature of your water bath. We just need to make sure that the units inside this equation match that of the gas law constant R. So this is the R that we're going to use, and you can tell by the units, it kind of gives you a hint of the units of the other variables. Pressure needs to be in atmospheres. Volume has to be in liters. Temperature has to be in Kelvin so that moles N comes out of this equation. So just make sure that the units you're putting in PV equals nRT are good. This is the equation you're going to be using over and over in that lab, plus a little bit of stoichiometry. All right, so that's just a little recap for the gas lab that you will all be doing. And then now let's move on to chapter 9. Okay, so chapter 9. So far, we've only drawn molecules flat. All right, so like this molecule, SO4 2-. We draw it flat, but do you think this molecule is flat in real life? No, it's not. And that's what we're going to explore in chapter 9. Electrons are not dots on a page. They exist in 3 dimensions in real life. All right, so just because we draw a molecule flat on paper doesn't mean it's flat. Right, so electrons are not dots on a page. And we're going to use these ideas of molecular shape to then relate them to, oh, you got some pumpkin. Relate this to properties that we see. Shape is directly related to chemical properties that we'll talk about in chapter 10 and 11. And then finally, because in chapter 8 we talked about basics of chemical bonding, ionic bonds, covalent bonds, whatever. The last part of this chapter, we're going to learn advanced theories of chemical bonding. So we're going to learn something advanced, all right? But that's not until probably Thursday. First, we're going to talk about shapes and polarity in this section. Okay, so what do molecules look like? Okay, the basics here is just because you draw the molecule flat in its Lewis structure does not mean that this molecule is flat. So for example, this is carbon with 4 chlorines on it. This is what its Lewis structure would look like. These bond angles are not 90 degrees. Just because you drew it 90 degrees on paper doesn't mean it's that way in real life. And so this kind of gives way to the secret of chemistry we talked about previously. Its composition and structure dictates chemical properties that we see. And so this structure, we're looking at, okay, what do these molecules look like structurally that lends itself to the properties that we see? And so that's why it's important in those properties that we see to understand what do molecules look like. So there's some interesting things here of, ways molecules can shape themselves. So here's an example of a molecule with a central atom and 2 atoms bonded to it. So this molecule can actually adopt many different shapes, that the 2 B atoms can be linear to one another, 180 degrees from one another, or they can be in a bent arrangement. And there's a way we can predict that. Or in this example, AB3, so 3 outer atoms around our central atom. There's a lot of different ways that those 3 atoms can arrange themselves. And again, there's a way we can predict how we understand those atoms arrange themselves. So here, they can be flat with one another. The 3 atoms can make a pyramid, or they can make a T shape. There's a very systematic way we can determine shape. So molecules can have similar formulas, but different shapes. That's where VSEPR theory comes into play. So VSEPR theory stands for valence shell electron pair repulsion. And that's the big idea within this section to predict molecular shapes. Electrons, they have a charge, right? What charge do they have? They're negative. And so if all electrons are negative, electrons repel one another. That's the big idea. Electrons repel one another. But in a molecule, what are bonds made out of? What are bonds made out of? How do you make a bond? There's 2 electrons in it. Yep. So in a bond, there's 2 electrons. What's a lone pair? Also 2 electrons. So the big idea here is that bonds repel one another and lone pairs repel one another. They all repel one another because they're all made of electrons. So the big idea is we want to count how many electron domains are there around a central atom, and then understand that those electrons repel one another, and that gives us our electron domain geometry, which is our template for our molecular geometry. So we have to consider both bonds and lone pairs, and that's in here, right? The electron domain around your central atom includes the electrons that are in bonds, so bonding domains, and electrons in lone pairs. So we got to start with that first. That gives us our template for our molecule. But when I ask you, like, what is the shape of this molecule, what is its molecular geometry, I only want you to tell me where can I find atoms. But the thing is those electrons still influence the shape of the molecule. So that's where molecular domains or molecular geometry comes from. We need to think, and you need to tell me where are the electrons just in bonds, where are those atoms actually reside. Right? And so we're going to first start with electron domains because this gives us our 5 parent shapes. And they're listed right here, but I also have them down here in this table. All right? So depending on how many electron domains are around your central atom, so you want to count how many bonds are there to the central atom and how many lone pairs. That number will tell you the parent electron geometry shape you need to start with. And so there's 5 here. Linear, when there's 2 regions of electron density, those 2 regions will spread out as much as possible to give those electron domains as much space as possible. I like to think of electrons as like siblings who hate each other, and they want to get away from one another as much as possible to give each other enough room. But once we get to 3 electron domains, so 3 siblings trying to share the same space, we see the shape changes to trigonal planar, where all of the electron domains are 120 degrees from one another. All right? Then we get to 4. 4 gets a little bit more complicated, where those 4 electron domains now have to spread out in 3 dimensions, and we make a tetrahedron. Right? And then these bond angles are 109.5 degrees away from one another. So that's 4 electron domains, so it becomes like a 3-dimensional object. Versus trigonal planar, it's flat. Okay? But 4 electron domains is tetrahedron, that it takes up 3 dimensions. Then 5 electron domains, we get trigonal bipyramid, and you see that up here. All right? So remember, electron domains can be bonds or lone pairs. This is the template we're working with. And then we'll see in a little bit that with trigonal bipyramid, there's different spatial requirements for where electrons can go. And then our last, most complex one is octahedron with 6 electron domains. All of these bond angles are 90 degrees from one another. So this is how we can get those negatively charged electrons, reducing their repulsions by spreading out as much as possible. And that's how 6 will be arranged the most effectively. So these electron geometries, I like to call these the parent geometries, right? Because once we start putting lone pairs on things, we take these electron geometries and then we just erase where lone pairs are, all right? That's how we get to our molecular geometry. We understand that lone pairs, we can't see them, but we can see the atoms themselves. So if we have a molecule with 3 electron domains, but one of them is a lone pair, what we want to do is just erase that lone pair and ask ourselves what shape is left over. This is bent, yes. Or if we have, let's say, a tetrahedron, this is kind of difficult to see, but if we have a tetrahedron electron domain geometry, but 2 of them are lone pairs, we literally erase 2 of the lone pairs, and we ask ourselves what shape is left over. This is also bent. So what a lot of students do is they kind of switch between these electron geometries, but these geometries are always the template we work with, and then place lone pairs as necessary to get those shapes. And that's what I'm talking about in this slide, where these are how we get our molecular geometries. Now we need to consider lone pairs. So if we have molecules that have no lone pairs, all those geometries, those parent geometries, they're tried and true. That a molecule with 2 bonds and 0 lone pairs will be linear. A molecule with 3 bonds, 0 lone pairs will be trigonal planar, and etc. But it's once we start putting lone pairs on our central atom, taking up some of those electron domains, that's where we just start erasing certain parts of our original electron domain parent geometry to give rise to what molecular shape is actually left over, right? So we'll be referring to these tables and these shapes. These other shapes that are made from the parent geometries, the name tries to tell you what shape it is. But also what we need to know are bond angles. So in this slide shows you the different ideal bond angles for these electron geometries. So do memorize these. All right, so 2 regions, this is 180. 3 regions is 120. In a tetrahedron, it's 109.5. In a trigonal bipyramid, in the pyramid part, they're 120, and then there's another bond angle that's 90, that's up and down, and then in an octahedron, everything's 90. So we'll come back to these ideas when we talk about bond angles. But let's just see if we can do electron geometry. So we'll come back to these. So these are the 3 steps to determine a molecule's geometry. All right? So the first step is, if you aren't given it, draw the Lewis structure. So obviously that first step may be 6 steps, the 6 steps from chapter 8. All right. Then to figure out the geometry, we want to just focus on the central atom. And that's where that atom, we want to count how many domains are around that central atom. All right. So once we focus on that central atom, we count the number of electron domains to get that electron geometry. So again, this means we count bonds, bonding domains, and lone pairs to get that number. And then that's how we get our parent geometry. That's our template. Then the last step is to consider lone pairs. Once there's lone pairs on your molecule, you just want to cover up parts of your template and then tell me what shape is left over. All right? If there are no lone pairs in your molecule, then we don't even have to do step 3. All right? Okay. So those are the steps. Write it down. Write it down. So in the next 2 slides, we will go through a bunch of examples, and I have the Lewis structures for you. And so we'll just focus on how can we get these shapes given these Lewis structures. All right. Okay. Okay, I'm going to change the slide now. All right. So, okay, let's go through these molecules one at a time. So the first step is draw the Lewis structure, but we have all of those. So the next step is we want to focus on our central atom. So in ammonia, NH3, that's the nitrogen atom. So I like to just inventory what's on that nitrogen atom. It looks like there are 3 bonding domains and 1 lone pair. So what is the electron domain number? 4, yes. So we have to count where are electrons. We have electrons in 3 different bonds, and we have electrons in a lone pair. They all count towards our electron domain number. And it's so through that number we can tell what the electron geometry is. So you go back to the slide. What is 4 electron domains? So 4 electron domains that spread out as much as possible will give us what shape? A tetrahedron. Yes, so do remember that, okay? We do need these shape names. All right, so this is a tetrahedron. So that's our template that we're working with. All those electron domains, they're going to spread out 109.5 degrees away from one another. So I'm just going to draw this in as 3-dimensional as I can. So that's our tetrahedron. 4 electron domains. So the 3 bonds and the 1 lone pair, they're spreading out in these different directions. Right? That's our electron domain geometry, but that's not our molecular geometry. We can only see atoms. We can't see lone pairs. So the idea here is we need to now account for that 1 lone pair that's present. So what I do is I just place the lone pair somewhere. I'm going to place it right there. And understand that I can't see that. I can't see it. So all I'm going to do, I'm just going to erase it. And I'm going to ask myself what's left over. What shape is left over once I erase 1 leg, which is that 1 lone pair? What's left over? This is called trigonal pyramid. It's not trigonal planar because we see that those 3 legs, they're still standing up. So what does not happen is when we erase that lone pair, it doesn't mean the lone pair went away. It just means that we can't see it. So what we see is what bonds are left over in that same arrangement. So this shape that is left over is a trigonal pyramid. Because that lone pair is still there, we just can't see it. So if we include the lone pair, everything's a tetrahedron. But then we literally cover up where that lone pair is and we ask ourselves what shape's left over. That is a trigonal pyramid. Okay, so let's keep going. All right, CH4. How many electron domains? 4, because there are 4 bonds. 0 lone pairs. So what electron geometry is that? It's tetrahedral again. So I'm going to draw it. So tetrahedral. Okay, there we go. Are there any lone pairs we have to worry about? Nope. So if there's no lone pairs, there's nothing we have to cover up. So that means our molecular geometry is the exact same because all of the electron domains are bonding domains. So our molecular geometry is also tetrahedron. All right, because there was 0 lone pairs we had to consider versus the previous one, there was 1 lone pair we had to consider. All right. I'm just going to skip these ones. I'm going to go to water, and you'll see why I want to do water. Because if you count the number of electron domains around water, how many are there? 4 again, yes, 4 electron domains. But this time, there's 2 bonds and 2 lone pairs. All right? So since the electron domain shape is still 4, that means the template we're working with is still a tetrahedron. All right, so we want to start with that tetrahedron shape. So 1, 2, 3, 4. All right, 4 electron domains, but this time, how many lone pairs do we have to consider? 2 of them. So I'm just going to draw them on that tetrahedron. So let's make them gray. So I'm going to put them here and here. So 2 of those electron domains are lone pairs. And so you just squint your eyes, pretend you can't see the lone pairs, and tell me what shape is left over. Bent, yes. So it is not linear. Because what a lot of students will think is, oh, okay, it only has 2 bonds, so that's a linear arrangement. But the idea here is that linear does not superimpose on a tetrahedron. We still adopt that electron geometry shape, where the lone pairs just template themselves on that existing electron geometry. So again, what I like to do is just literally erase those 2 lone pairs and ask myself what's left over without moving the other bonds. So in this case, it is, because we took into account 2 lone pairs, this is a bent arrangement, right? So all 3 of those molecules, ammonia, CH4, and water, all have a tetrahedron electron geometry, but just different numbers of lone pairs to consider, all right? So even though I draw ammonia flat, even though I draw CH4 flat, these molecules are not flat. They do adopt these tetrahedron shapes. All right, so let's do some other ones with other geometries. Okay, O3, again, we want to focus on the central atom. So in this case, it's this oxygen. All right, and so I kind of skipped over this before, but when we calculate electron domains, it's the bonding domains plus any lone pairs. So what I mean by bonding domains, I'm careful with my language, and I don't want to say how many bonds are there, because the idea here is this double bond has how many electrons in it? 4, yes, while the single bond has 2. But the thing is that in a double bond, all 4 of those electrons, they travel together. They stay together in one bonding domain. So a single bond counts as one domain. A double bond counts as one domain. A triple bond counts as one domain because all of those electrons stay together. So in this example, there are two bonding domains and 1 lone pair. So this electron domain number is 3. All right, so the idea here is when we count bonding domains, a single bond, a double bond, and a triple bond, they all count as 1. And it's because in those bonds, all those electrons, they remain in the same domain, in the same place. All right, so these 4 electrons, they travel together. So since they travel together, they're going to move as a pack within our electron domain geometry. All right, so this has an electron domain number of 3. Because there's 2 bonding domains where the single bond counts as 1 and the double bond counts as 1. So let me just go 1, 2, 3. That's how we count it, right? So the double bond counts as 1 domain. Yes, that's why I'm careful with my language and I don't like to say how many bonds are there. I always say bonding domains. All right, so there's 3 bonding domains. So what shape is that? Or sorry, 3 electron domains. What shape do we call that? Trigonal planar, yes, planar. So that's the electron domain geometry. So that will adopt this shape where everything's 120 degrees from one another. But are there lone pairs we need to consider? Yes, so we draw them in. And then to get the molecular geometry, we just squint our eyes and pretend we can't see those electrons. So what shape is left? Bent. Yes, it is bent. The lone pair thing. So when we, so these 2 electrons travel together. It's just like in ammonia, these 2 electrons travel together. Yes, only the central atom, yes. So we're only looking at the central atom. I don't care about these electrons. I'm only looking at the oxygen in the center here, just like in carbon, I just was looking at the carbon. In nitrogen, in ammonia, I was just looking at that nitrogen atom. Okay. All right, so we said it's bent. Bent with about what bond angle, you think? So look at so think about the electron geometry parent structure it came from. It's 120. Yes, this bent arrangement is going to be about 120 because it came from a trigonal planar template, all right? Because there's more than one way to get bent, and we'll see that in a little bit. Okay, so SF4, let's look at this one. How many electron domains? 1, 2, 3, 4, 5. So 5. Where 4 of them are bonds and 1 is a lone pair. So what does 5 mean? Trigonal bipyramid. Trigonal bipyramid. It's on the table. It's on the table. All right? So it's the 5 number we care about. We don't care about the 4 bonds. This shape is not tetrahedral. We want to use trigonal bipyramid as our template in this case. So if I draw a trigonal bipyramid, it's going to look something like this. All right? Those are my 5 electron domains. Okay. How many lone pairs do I have to consider? 1. So I need to draw 1 lone pair. And for now, I'm just going to tell you, and just believe me for a second, that the lone pair is going to go right here. It's going to go right there. And I'll tell you why later. All right. The lone pair is going to go right there. And so when we talk about the molecular shape, we literally erase that lone pair, and you tell me what shape is left over. What does that look like? It's on its side, I guess. It's a seesaw. It's a seesaw. If you kind of bend it over, those 2 in and out legs become like the middle of the seesaw. All right, so this is a seesaw. Got it? All right, let's do a little bit more. We did water. We said that the 2 last bonds make a bent arrangement, but does this bond angle, is this bond angle what 120 degrees like our other bent arrangement? We said this one was 120. Is this one 120? No. What bond angle is it going to be about? 109.5, because its parent geometry. Its electron geometry came from a tetrahedron. So this bent bond angle is going to be about 109.5. Yeah, so there's more than one way to get a bent arrangement, so this one's just going to be a little bit closer together than our other bent one. Okay, so let's keep going. The nitrogen. What is its electron domain number? 3, yes, where the double bond counts as one bonding domain, and the 2 single bonds count as one bonding domain, so it's 3. So what shape is that? Trigonal, planar. And so I can draw it, boop, boop. Are there any lone pairs we have to consider? Nope, so it's 0 lone pairs, so what does that mean in terms of its molecular geometry? It's the same, so it's also trigonal planar. Very good. Everything stems from the electron geometry. All right, let's keep going. And so you see here the way that I draw nitrate, see how in the Lewis structure, sometimes I try to show what it looks like. So in nitrate, I made all the bond angles 120 degrees from one another because that's what the shape is. But remember, Lewis structures don't have to convey shape and still be correct. So here, in this case, water. This is a correct Lewis structure of water, but how the bonds are arranged, like those hydrogens are not 180 degrees from one another. But yet this Lewis structure is still correct. It requires us to use Vesper theory, go one step further to get that molecular shape. Okay, so on that same vein, BF3, these are not the bond angles. They are not 90 degrees from one another. We have to apply Vesper theory. So how many electron domains? 3, so this is what shape? Trigonal planar. Are there any lone pairs we need to consider? No, so that means it is also trigonal planar. The molecular geometry, because there are no lone pairs, so it's going to look like that. So all the fluorine atoms are 120 degrees away from one another. All right, last one, SF6. Electron domain? 6. So what shape is that? Octahedral. So how I like to draw octahedron, I draw them like this, right? So are there any lone pairs we need to consider? Nope. So that means its molecular geometry is the exact same. It's an octahedron. There are no lone pairs I have to place on there. Yeah?
So not for this one specifically, but the other ones where you have to like take off the lone pairs, how do you know which one to take off?
Take off.
When you like erase or
Yes. Yeah, so you're asking, okay, let's say we start, let me go to like one of these. Okay, we'll just do that. So let's do a trigonal planar. Let's pretend I want to put one lone pair on there. It actually doesn't matter. This one, it doesn't matter where I place the lone pair, because if I erase this leg, it's bent. If I erase this leg, it's bent. If I erase that one, it's bent. So if we go to a tetrahedron, it's actually the same thing. So a tetrahedron looks like this. All right. So if I put one lone pair on a tetrahedron, technically that is still trigonal pyramid. It's just kind of facing this way. This leg, same thing. It still makes a trigonal pyramid. If I erase that leg, it's still a trigonal pyramid. It's just going the other way. So in this example, I can take off any one of the legs and I still make the same molecule.
So for the seesaw one, if we took off a random.
Can I just come back to that a little later? Yeah, I promise. I'll come back to the seesaw one. Yes. All right. So just have some faith in me. Okay. So let's talk about those bond angles. So in an octahedron, so in this molecule, what are these bond angles? What's this bond angle right here, you think? Right there. This is something you should know in addition to the names. Also know those ideal bond angles. What is that? They are 90 degrees. I mean, you can also kind of logic your way into it. You can think, oh, this makes a like cross. Like these two bonds make a cross, and two crosses, you'll have a 90-degree quadrant in each side, right? So that is 90 degrees. What about in trigonal planar? If you cut a circle into 3 slices, each slice is 120. Tetrahedral, that's maybe a new one that we haven't talked about before, or you talked about in geometry, but this one is 109.5. all right? And then in a linear geometry, this is 180. So these are all very important bond angles in addition to the molecular shapes you need to know. So those numbers we just went over, 180, 109.5, 120, 90 degrees, all of those are what I call the ideal bond angles. All right, we're also going to see slight deviations from these ideal bond angles, and it all stems from the idea that we can have electrons exist in different places. They can be in bonds, they can be in lone pairs, they can be in double or triple bonds, and all of these electron domains, they have different space requirements. And so in your head, just think that when you compare how much space a single bond versus a lone pair takes up, a lone pair is big, fat, and juicy, and it just takes up more space than single bonds. And that's how you can predict deviations from ideal bond angles. Lone pairs just take up more space. So if we look at this example, so CH4, NH3, water. We already said that all of these have tetrahedron electron geometries. So they all have that ideal bond angle of 109.5. But what we actually see is that we only see exactly 109.5 in CH4, where all of the bond angles, all of the bonds are CH bonds. There are no lone pairs, 0 lone pairs. All of those bonds, they're equivalent to one another. But it's once we start putting lone pairs on our electron geometry, those lone pairs, they're just big, fat, and juicy, and they take up more space than single bonds. So what happens is that lone pair just pushes all the other bonds a little bit closer together. So what we actually see for ammonia is not 109.5, but just something a little bit less, 107, sure. All right, so now let's put 2 lone pairs on a tetrahedron. So now we have 2 big, fat, juicy lone pairs on a tetrahedron. And so those lone pairs, they're going to push those hydrogens a little bit closer together. And so we're going to see a slight deviation away from the ideal 109.5. And so instead, we're going to see about 104 instead. So 2 lone pairs will deviate it even more than 1 lone pair like our ammonia idea. All right, and so yes, the big idea here is that lone pairs, they're just larger than a covalent bond. So they're going to just push the other bonds a little bit closer together. And so we can predict bond angles this way. We can say, oh, like the bond angle will be like a little bit more or a little less than the ideal. So just memorize those ideal bond angles and how lone pairs can affect, deviate those ideal numbers. Okay, on that same idea, multiple bonds can also deviate bond angles. So let's look at this central atom. That carbon atom has how many electron domains? 3. So what shape is that? Trigonal planar. And what is the ideal bond angle in a trigonal planar? 120. Okay. But do you think those bond angles are all exactly 120? No, they're not. And this is the reason. So just like we said, lone pairs take up more room than a single bond. Let's think about it this way. What do you think takes up more space, a single bond or a double bond? A single bond is made up of how many electrons? 2. A double bond has how many electrons? 4 electrons. So in that same idea, which one's going to take up more room? It's the one with 4 electrons. So just like we said, lone pairs are like big, fat, and juicy and take up more space. Double bonds also, for that same reason, will deviate our ideal bond angles and push some bonds closer together. So this double bond just takes up more space. So therefore, it pushes these 2 bonds closer together. All right, so what do we think this indicated bond angle is going to be? A, B, or C? B, yes, slightly less than 120. But what if I didn't say that bond? What if I wanted you to tell me, okay, what do you think this bond angle is? The pink one. It's going to be slightly bigger than 120 because it's adjacent to the big, fat, juicy double bond. Yeah, okay. So reference yourself to the ideal bond angles, right? And then just apply the idea, oh, lone pairs, double bonds, triple bonds, they take up more room. Okay? Then let me look at this. How about this one? Let's see. CO2. Will this have deviations to ideal bond angles? No. Why won't this have deviations? It's symmetric. Yeah, that both are double bonds, right? So yes, this double bond is big, fat, and juicy. So it's, but how about the other side? It's also, so it's going to look like that. So here we're going to see a bond angle of exactly 180 degrees. Yep. Okay. Also, if you're already 180 degrees in terms of bond angle, can you get any further away from it? No, you can't. All right. So even if we had a molecule that looked like this, like a triple bond and a single bond, this bond angle will also be 180 degrees, because even if that triple bond was big, fat, and juicy, there's still no way that single bond can get any further away from it. 180 is as far away as it can get from it. Okay, all right. Okay, so let's, I told you resonance was gonna come back. Okay. This is nitrate. This is our like prototypical resonance structure. Does nitrate have one short bond and two long bonds? No, it doesn't. It doesn't. It has a bond order of what? Nitrate. We calculated it before. It has a bond order of what? 1.5? No, 3. Yes. So it's 4/3. 4 bonds moving over 3 different positions. Okay. So with that in mind, and the idea of deviations from bond angles, ideal bond angles, what do we think the bond angles between the bonds in nitrate will be? What do we think they are? So like these bond angles. Are we going to see, 2 big bond angles, 1 short bond angle because there's 1 double bond? Or are we going to see all bond angles that are exactly the same? What do we think? So take a second, think about it, and discuss it with someone next to you. Yes. Ask yourself, does that double bond exist? Does that double bond exist? And maybe that'll help you with your answer. You got it? Yeah. Okay, so we just learned about deviations from bond angles. So this double bond is going to take up a lot of room and do this, right? Yes or no? No, it's not going to do that. It's not. So who says A? Okay, good, half of people. And then who says B? That would be right if it was the previous example where we said, oh yeah, double bonds, they take up more room than single bonds. But that double bond doesn't actually exist. We just calculated that the bond order of the nitrogen oxygens in all of those NO bonds, it's actually 1.33. So all of those bonds are identical. So we don't have this localized double bond present there. It's actually, smeared across the entire molecule. So the bond angles are all actually exactly the same. They're all exactly 120 degrees because that double bond doesn't actually exist. It's just easier for us to draw it this way, all right? But that double bond doesn't actually exist. And so, yeah, this is the idea of resonance. Resonance, the delocalization of the electrons in a double bond, they mess up bond order, they mess up bond enthalpy, bond strength, bond length. They also mess up bond angles. So for example, if I showed you this molecule, okay, this molecule, okay, does that molecule undergo resonance? Does that? No, it doesn't. So that double bond is localized. So what is this bond angle predicted to be? Slightly more than what number? 120, yes. Even though I drew it like 90 degrees, this Lewis structure isn't necessarily right in terms of its shape. We know this molecule actually looks like this, but the double bond is taking up more room, and so it'll push that, it'll open up that bond a little bit more. All right, so in this example, formaldehyde does not undergo resonance. So we do see deviations in bond angles, but not in nitrate, because nitrate doesn't have a double bond. It has 3 bonds that are all the same bond order. Okay, so let's estimate what these bond angles are in these separate atoms. So the strategy here is we want to do each atom one at a time, or each bond angle one at a time, and we want to focus on the central atom that contains that bond angle. That's what we want to focus on. So we have to do each of them but separately. All right, so the strategy here is, okay, for this first oxygen atom, let's determine the geometry first. Let's get the ideal bond angle first, then apply any deviations. So that oxygen has 2 bonds, 2 things bonded to it, but then it also has 2 lone pairs. So what is its electron domain geometry? Tetrahedral. Yes, tetrahedral. What would its molecular geometry be then? Bent, yeah, because that's 2 lone pairs. But we actually don't need that information, but we actually just need tetrahedron, because we know in a tetrahedron, its ideal bond angles are what? 109.5. And so that's our ideal bond angle, but is that oxygen going to have an ideal bond angle? No, because lone pairs, they're big, fat, and juicy, and they just take up more room. And so what is this bond angle probably going to be? Not 109.5, but just slightly more or less? Less, yeah, so it's going to be slightly less than 109.5. Okay. So like 104 or something, I don't know, like 104. All right, so then we do the same thing for the next atom and ask ourselves, how many bonding domains are there? 3, any lone pairs? Nope, so it just has an electron domain of 3, so what shape is that? Trigonal planar, and the ideal bond angle there is 120, all right? Is there anything present that'll mess up that ideal bond angle? Yes, that double bond. So that double bond just takes up more room. So where bond angle 2 is, does that double bond expand that bond angle or contract it? Expand it. So what is the estimated bond angle? Slightly more than 120 degrees. All right? Okay, and then we look at atom 3 or bond 3. So what is our electron domain geometry for that carbon? It's 3, so it is trigonal planar. So it's 120 degrees again, but we need to be careful of where the arrow is. So this arrow, is it being expanded or contracted by that double bond? It expands, so it's going to be slightly greater than 120 again. All right, versus like if I asked you if like bond angle, let's say this is bond angle 4, what would bond angle 4 be? Slightly less than 120. Yep, and that's it. Okay, so always start with those ideal bond angles. Okay, so count bonding domains, count lone pairs, get that electron geometry, get that ideal bond angle, then apply, okay, lone pairs, double bonds, it's going to mess it up a little bit. So think about those 2 domains just taking up a little bit more space and messing up those bond angles. Okay, so the question was earlier, how do we know where to place lone pairs on stuff? But what did we just learn? Lone pairs in comparison to bonds take up more room. So the question earlier was, where do I put lone pairs on, let's say, a trigonal bipyramid? So we want to utilize that same idea. Lone pairs take up more room. So we want to place lone pairs in a place on your electron domain geometry that gives it the most room. Right? So what's special about trigonal bipyramids is that there are 2 different spatial areas of a trigonal bipyramid, and they're not equivalent. So this is our trigonal bipyramid. So I like to think there's the axial positions on our trigonal bipyramid, the up and down places. They're 180 degrees from one another. But then the last 3 positions, These 3 positions actually make like a trigonal planar arrangement. We call this the equatorial region. I like to call it the belt of the molecule. So we have the belt of the molecule has 3 bonds, and then the up and the down are the last 2 bonds. So we see there's actually different spatial things present in those 2 positions. So like the axial position. So this red atom, that's the axial position. That axial position, if you think about its nearest neighbors, this red atom, white atom has 3 other atoms that are 90 degrees away from it, right? Okay, the axial atom. But then if we look at an equatorial atom, a red atom, see this red atom, actually it has 4 nearest neighbors, right? But this atom has 2 that are 90 degrees from it and 2 that are 120 degrees away from it. Right? So there's different spatial requirements or different spatial regions on this trigonal bipyramid, and that's important when we place lone pairs on our electron geometry. We want to put those lone pairs where we give those big, fat, juicy electrons as much room as possible. So if you had the choice of picking a room that was axial or equatorial, which one would you pick? Equatorial. Equatorial has more spatial room because your nearest neighbors are 120 degrees away from one another, and that's what happens when we place lone pairs on a trigonal bipyramid. So here's the parent structure. Everything's a bond, 0 lone pairs. But once we put 1 lone pair on the shape, see how it adopts in the equatorial region? The second lone pair that we place also goes in the equatorial region because it gives you the most space. That lone pair has the most space, has the most room. So then once we're left with this T shape, so remember the molecular geometry looks like that, and what's left is a T shape. If you had the choice of where to put that last lone pair, you'll want to put that last lone pair as far away from these other lone pairs as possible. So we see that third lone pair actually goes also in the equatorial region. So we see within our trigonal bipyramid, when we place our lone pairs, they preferentially take the equatorial region because that reduces repulsions within our lone pairs. All right, and so remember with these electron geometries, these are our templates. So to get what the molecular, to go from electron geometry to molecular geometry, we just ignore the lone pairs. So I like to just literally erase the lone pairs. When there's 1 lone pair, we see that the shape that is left over is a seesaw. So like an up, down, and then 2 little legs to the side. When there's 2 lone pairs, we see that there's a T shape left over. And what's interesting, when there's 3 lone pairs and 2 bonds, we see what's left over is linear, all right? Okay, so that is 5 electron domains. Electrons, they're big, fat, bulky, they want the most room. So in that same vein, we can predict what are the shapes in 6 electron domains, and then we start placing lone pairs on it. So in a octahedron, are there different spatial areas of an octahedron, or are all the bonds the exact same? They're all the same. All of them are 90 degrees away from their nearest neighbor. There's no axial or equatorial region. So when we place our first lone pair, does it matter where we put it? No, because all the bonds are the exact same. So I think in this example, they just put it on the bottom, but it doesn't really matter. All right, so we're just gonna put that lone pair somewhere. All right, so this is 5 bonds, 1 lone pair to make 6 electron domains. So if we wanted the shape, we just erase that lone pair and we ask ourselves what shape is left over. It has a square base and a little TP, so it's a pyramid but square, so square pyramid. That's 1 lone pair. All right, so now the question is when we place the second lone pair. The first lone pair we put in the basement. The second lone pair, electrons repel one another. Where do we want to put it? We want to put it in the penthouse, all right, of this molecule. We don't want to put it in those middle rooms. We want to put it at the top. Because if we put that next lone pair in the top, then these 2 lone pairs, they are as far away from one another as possible. And that's what happens. That second lone pair goes up top. All right, goes up top, so those two lone pairs are as far away from one another as possible. Okay, and so this is how we get our next shape with two lone pairs. If we erase those lone pairs and ask ourselves what bonds are left over, we have a square planar. Yeah, square planar. Okay, all right, so now let's pretend we want to put a third lone pair on it. Does it matter where we put it? Matter where we put it? Nope, now they're all equivalent. All those bonds are equivalent again. So if we want to put a third lone pair, let's just put it right there or something. All right, and that's what happens here. Okay, they put it back there, whatever. Okay, they put it over here. They put it right there. But all those positions are equivalent. And then we see that third lone pair is back there. And so if we erase those lone pairs, we see what shape is left over. It is, what does that look like? T. It's a T shape. All right, so 3 lone pairs, 3 bonds will also give us a T shape. All right, and so now once we have 3 lone pairs, what if we want to put a 4th lone pair on? Where is it going to go? It's going to go right here. Yes, because putting it right here maximizes, puts all of those lone pairs in one plane. And that reduces the amount of repulsions that are there. That this, if I put it right here, there's only 2 other lone pairs that it's adjacent to. All right, and so those are that's our last shape. And we see if we like just erase those shapes, we're left with that linear shape. All right. Okay. So let's look at these shapes. Tell me, what are the ideal bond angles in a octahedron? What is it? So this bond angle right here. That is 90. Okay, great. What if I put a lone pair on it? Is this still 90? Nope, it's going to be a little bit off from 90. It's probably going to be what? A little bit less than 90 because of that lone pair that's there. All right. Okay, now let's go to this molecule. Is this bond angle right here, is that 90? Now we have lone pairs present, but what's special about those lone pairs? They cancel each other out, don't they? So that square planar arrangement will be exactly 90 degrees because those 2 lone pairs cancel each other out. What about here? Are we going to see deviations in this molecule? Yes, we will see deviations away from 90. What about in this one? Will we see deviations? No. And so what you kind of did in the back of your head was apply the idea that, oh, those lone pairs have vectors. Sometimes the vectors cancel each other out. And when they cancel each other out, we don't see deviations. And that's the idea. The next idea is molecule polarity. That once we have polar bonds on a molecule, they actually exist in 3 dimensions, and we can get whether a molecule is polar or not by understanding that these bonds exist as vectors as well with their bond polarities. So just to overview, yes, you do need to know all the shapes, names, and all the bond angles for all of these different parent geometries, plus its lone pairs, all right? But the trick is with bond angles, just know those ideal bond angles, and I apply the idea of deviations with lone pairs and double bonds. So do know the geometries, bond angles, and now what we're gonna do is think about these molecules and their bond dipoles existing as vectors and thinking, do they cancel or not in 3 dimensions? All right, so I don't teach math, so I can't really teach vectors because like, doesn't that require like sines and cosines and stuff like that, right? To see if vectors add up. But in chemistry, all we care about is, do the vectors cancel or not? If they cancel, then you have a nonpolar molecule. If they don't cancel, then you have a polar molecule. That's all we care about. So I use a strategy called babies versus bodybuilders. Instead of thinking about vectors, think of your atoms on your geometry, pulling on that central atom. If they're in an arrangement that makes that central atom move, then your vectors don't cancel, and it's a polar molecule. But if they're arranged in such a way where the atoms do cancel each other out, where if both atom pulls on the molecule the exact same way, like 180 degrees from one another, then the central atom doesn't move, then that's a nonpolar molecule. So that's just kind of like my fake way of just inspecting vectors without actually calculating anything. And that's what I call babies versus bodybuilders. All right, so strategy for molecule polarity. First, we need to start with the Lewis structure. We need to predict the shape. Then on the shape, you need to understand that the atoms in those bond angles, they're pulling on the molecule. All right, and so, use the babies versus bodybuilders thing to determine, do the vectors cancel or not? Do those bond dipoles that exist on your template, do they cancel or not? So if we look at two examples, CO2 versus H2O. So if we look at the difference in electronegativity of a carbon and an oxygen here, we see that the difference is about 1. So we see that CO has polar bonds in it. This CO bond is polar, this CO bond is polar. If we look at water, its difference in electronegativity, so between a oxygen and a hydrogen, what is that? 1.4. So is an OH bond polar? Yes. So both of these molecules are polar. Both of the molecules contain polar bonds in them. But one of the molecules is nonpolar, one is polar. And it has to do with the idea how the bonds are arranged in their molecular geometry. So I like to think of it like this. Okay, these two oxygens make these bonds polar. Both of those oxygens are pulling on that carbon atom, but they're both oxygens, they're identical. So if they pull on that carbon atom 180 degrees from one another, does that central atom move at all? No. Because they're oriented 180 degrees, each oxygen is identical. So they cancel each other's vectors out. So we see that CO2 is actually a nonpolar molecule, even though it contains polar bonds. Versus if we look at water, right, water contains polar bonds, but the bond angles are different, they're bent. So if you have two babies fighting over a toy and they're both on the same side of the toy and they both pull on it in the same time, does that central atom or does that toy move? Yes, if they're both in that bent arrangement. So we see that water does have an overall dipole moment. It is a polar molecule because their bond dipoles do not cancel, right? So we see that water is a polar molecule, but CO2 is not, all right? So let's use the idea of babies versus bodybuilders, okay, in these examples. So tell me, are these polar molecules or not? So remember, polar means that their vectors do not cancel. But a non-polar molecule, your vectors do cancel. So let's look at CO2 again. Okay, so you got two oxygens. Think about the arrangement, linear, 180. Do those vectors cancel? Yes, they do. So CO2 is a what kind of molecule? Nonpolar, but let me change it up real quick. So CO2 is nonpolar, but what if I had this molecule? What if it was a carbon? It was an oxygen on one side, but a sulfur on the other side. It's still linear. What is that? That would be polar, because yes, these atoms are 180 degrees from one another, but are they identical? No. So this would be an example where you have a baby on one side, and then you have a bodybuilder 180 degrees away from each other. Yes, they're away from one another, they're 180, but if they both pull on the central atom at the same time, is the central atom going to move? Yes, if both of the attached atoms are different. So in this molecule, so a sulfur and an oxygen attached to carbon, this would be a polar molecule because we don't have that symmetry. That the vectors are actually different sizes. So here, CO would be like a really big vector, and then CS would be a smaller vector. So this is what I mean by you have a baby on one side, and you have a bodybuilder on the other side. And so these vectors do not cancel the whole way. Okay, what about BF3? What do we think? So now we have, let's say, 3 bodybuilders all around this central atom, and they're all 120 degrees from one another. Do those vectors cancel? They do cancel, so this is a nonpolar molecule. Yes. So just imagine, you have a tire. You have 3 identical bodybuilders. They all pull on the tire at the same time, and they're all 120 degrees away from one another. Does that tire move at all? No, because their vectors cancel because they're all 120 degrees around that central atom, all right? So this is a nonpolar molecule, all right? So that's trigonal planar, or you can look at this picture. Look at this picture. So here, and you got 3 identical things all pulling on it at the same time. All right, what if we throw a lone pair into it? Lone pairs, bunch of electrons. So we see that that lone pair actually has a huge dipole moment. So it's like we threw in a bodybuilder in with 2 babies. And so is this going to be polar or nonpolar? It's going to be very polar, yeah, because that lone pair is going to screw everything up. Okay, screw up all those vectors. All right, tetrahedron, polar or nonpolar? Nope, it is nonpolar. We have 3 little babies, but yes, it's a little bit different because the 4 vectors, they're in 3 dimensions now. But remember, all these bond angles, they're identical. They're all 109.5. So yes, we have 4 babies all around, you know, a sphere, but all the bond angles are the same. So if they all pull in at the same time, then this molecule's not going anywhere, so this is nonpolar, okay? Because all of those bond angles are 109.5. Okay, let's throw a lone pair into it. So we got 3 babies in a bodybuilder. Is that going to be polar or nonpolar? Polar, yes, because that lone pair screws everything up. All right, what about bent? So 2 lone pairs. What do we think? Yes, very polar. Yes, 2 lone pairs. So 2 bodybuilders, 2 babies, right? That's going to be polar. Okay. All right, so let's keep going. Trigonal bipyramid. What do we think? Nope. It is nonpolar. Yeah, so let's think about the different regions of our trigonal bipyramid. We have the axial. So if you have 2 babies 180 degrees from one another, do those cancel? Yes, these 2 will cancel. Now let's look at the 3 down here. So if these 3 babies, they're pulling on the toy 120 degrees from one another, do those cancel? Yes, they do. So we see as long as the bonds or the atoms are the exact same, the top and bottom will cancel out with one another, and so will those sides. So this is a nonpolar molecule. Okay, what if we put a lone pair on it? Yes, that's going to be polar. That lone pair screws everything up. Okay, because now within the equatorial region, those do not cancel with one another anymore. What about 2 lone pairs? Also polar. So at this point, you may be thinking, oh, lone pairs will always make it polar. Nope. Let's look at the next one. That one. So look at this shape. Do these 2 cancel each other out? Yes. But what about the 3 lone pairs? They also cancel each other out. So this molecule that's linear is actually nonpolar. All right. So the 3 lone pairs do cancel one another out. Okay. So let's end, yes, on this slide. Right, the last one, an octahedron. So all 6 electron domains, they're the exact same, polar or nonpolar? Nonpolar, great. Now let's throw a lone pair in the mix. That would be polar because this lone pair is pulling unequally on that molecule. And then finally this one. Yeah, so look for symmetry, look for where vectors cancel one another. So these 2 lone pairs cancel. And then all 4 of those bonds cancel one another as long as the bonds are the exact same. All right, so this molecule would be nonpolar. All right, so we'll end there. We'll talk a little bit more about polarity and then move on to valence bond theory, some of our advanced theories of chemical bonding on Thursday.